All right, guys, so this is going to be your second online lab. In this lab, we're going to be talking about logic gates. So before we talk about, before we do get into logic gates, though, let's kind of distinguish between what we've been doing so far and what we're going to be doing going forward in all of these labs. So far, what we've been doing is talking about analog signals. So, as an example, right, let's say this is our equilibrium position there, and we have some sine wave. An analog signal is continuous, so it's constantly changing. So a sine wave, right, is an analog signal. So we can say that analog means continuous. And so when we're building analog circuits, right, we have to really worry about what shape this function takes. Okay. Now for digital, where this is your voltage, right, and this is changing is your time. Okay. Now for digital signals, they're much simpler. They're actually, instead of continuous, they're discrete. Meaning they can only take one of two values, or we only care about whether it's off or on, or 0 or 1, right? So a digital signal would look more like a square wave, right? Where if this is our equilibrium position, again, we would either have on or off. So our digital signal would look something like this. Okay, well, we're not too worried about what is the amplitude necessarily. We're not too worried about what the shape is. We're only worried about, is my signal a 1 or is my signal a 0? All right, and then feeding those signals into my circuit, how does that change, or how is that going to determine what my output is? Okay, so again, this is 1, and then down here would be a 0. Okay, so it can only take, for digital signals, it can only take one of two values. All right. Now, this brings us to logic gates, because what a logic gate does is, if we have our gate here, it'll take an input, most of the time two inputs, so we have input 1, and then we have input 2. And then depending on the type of logic gate that we have, we will get some output, okay? So this is our output. All right, and these input 1 and input 2 can only take one of two values, going back to this whole discrete description, right? So our inputs can only be 0s or 1s. Or you can think of this as being off for 0 or on for 1. Or in the case of switches, you can think of it as being closed, it would be open for 0 or closed for 1. Or in case of a logic gate, what we'll be talking about is false for 0 or true for 1. Okay, so all of these kind of sort of mean the same thing, but depending on the context that we're talking about, and one may make more sense than the other. Okay, so what we're going to be doing now is talking about different types of logic gates. So by changing this gate, we'll change this output depending on what these two inputs are. So what we have to do is make what's called a truth table, or a logic table. Okay, and the first gate that we'll talk about is called an AND gate. So we have AND, and we can have an input 1 or an input 2, and then we'll get some output. Okay, now let's go ahead and write down all of the possibilities that we can have, or all of the different combinations that we can have for input 1 and input 2, right? If it can take only 1 or 0, right? We have two possibilities for each one, and we have two slots that they can both go into, so we'll have 4 different combinations of 0 and 1, right? So for the first one, we can say 0 is one possibility, 0, 1 is one possibility, and then so forth, right? So these are the possible combinations that we can input into our gate. Now let's talk about what will an AND gate, now this is specific to AND, what will we get as an output? Now for all of these, you can kind of ask yourself a question, right? And for AND, you would say, is input 1 and input 2 true? Okay, now depending on your answer, that'll determine your output. So in this case, this first case, where they're both false, you would say, is input 1 and input 2 true? And since they're both false, you would say no, so that means my output will be false, right? And then going forward to the next possibility, you would say, is input 1 and input 2 true? And in this case, because input 1 is false, we would say that they're not both true, and so we would say that's false. And then similar logic, the next one would be false, right? And then for the final one, this final possibility, we say, is input 1 and input 2 true? And in this final case, that is the case, because both input 1 and input 2 are both true. So that means that our output would be a 1. Okay? So if we had some, say, LED or something hooked up to this output over here, we would only get a signal, or the light or the LED would only illuminate if both of input 1 and input 2 were on, or both of them were ones. Okay, so that's kind of how these truth tables work. We also have something for all of these truth tables. We can talk about their inverse. So and to denote an inverse, you just put an in front of whatever the gate is. So instead of an and, we can talk about a NAND. And for these inverse gates, right, the possibilities for the inputs don't change. So these inputs will always be the same, because they're just, we list all of the possibilities that we can have. What does change is the output, right? And since this is the inverse of my AND gate, the NAND gate, we can, anywhere where I see a 0 for the output, I write a 1. So these first three are all 1s. And then this last one, because it's a 1, is a 0. So you just take the inverse of the output, and that gives you the inverse of that particular gate. So we have a NAND gate where the output is 1, 1, 1, 0. All right, so let's just go through and talk about a few more important gates. These are by all means not the only gates that you can have, but these are the important ones. We can talk about an OR gate. So again, we have our N1, our N2, our output. These inputs don't change. All right, now we're talking about OR. So we want to know, is either or true? Okay, so for this first example for 0, 0, is either input 1 or input 2 true? No, because they're both 0, so our output would be false. Now for this next possibility, is either N1 or N2 true? Yes, because N2 is true, so we get a 1. Is either input 1 or input 2 true for this third one? Yes, because input 1 is true. And then finally, since they're both true, that means then yes, either input 1 or input 2 is true, so we also get a true on that one. Okay, so that's for an OR gate. And so similar to AND gate and NAND, you can also have the inverse of OR, which is a NOR gate. Output, right, where all of these inputs again are the same. And then our output is the opposite of our OR gate. So instead of 0, 1, 1, 1, we get 1, 0, 0, 0. All right, just two more gates to talk about here, and then we'll talk about actually building these gates, or ways in which we can build some of these gates. So the next one is called an exclusive OR. So an exclusive OR means either or can be true, but they both can't be true. Okay, so the only change from our OR to our exclusive OR is this final possibility where they're both true would be false, right? Because the exclusive OR means only one or the other, not both. So let's rewrite this real quickly. N1, N2, our output. So our output would be the same as our OR, like I was saying, except for this last one is 0. Okay, now I don't want to continue to just rewrite all of these, but for the exclusive NOR, which is the negation or the inverse of our exclusive OR, right? We can say N1, N2. I don't want to rewrite these inputs, so I'm just going to only write the output. It's going to be the opposite of this, so it's going to be 1, 0, 0, 1, right? Where the inputs are the same as all the other ones that we've been doing. Okay, now the final one is a little bit special of a case, right? Because in this one, we actually have only one input. So we have just an in, right? There's not N1, N2, there's only one in and one out. And so it's a NOT gate means that we just take whatever the input is and then output the opposite of that, right? So we say if our input is 0, then we're going to be outputting a 1. And then if our input is a 1, then we output a 0. Okay, so that's a NOT gate. All right, now all of these gates have different symbols, and you can look in your manual to see what those symbols look like. I'm not going to draw them all here, okay? But if you see one of those symbols in a circuit, you can refer to that table in your manual to see what gate is it referring to, okay? Now, we've talked about some of these important gates and the truth tables for these gates. Now let's talk about how we can go about building some of these gates, okay? So here are a few simple examples of some gates that you would have built and that you will be seeing in the next part of this video. What we're going to do now is kind of explain what the truth tables for these different circuits will look like, and from those truth tables we can determine what the type of gate it is. Okay, so in this first one here we just have two switches, so these are switches, right? If the switch is on, or if the switch is closed, that means I have a 1. And if it's off, or if the switch is open, then I have a 0. Okay, so let's write out our truth table here. Okay, now if both switches, S1 and S2 in this circuit, are both open, that means no current is going to flow through this circuit, and that means that this diode here, over here, this LED is not going to light up. Okay, so that means we're going to have no output. So our output is false, or our output is off, so we put a 0 there. All right, now if we leave S1 open because it's a 0 and we press S2, right, the circuit is still broken at S1. So again, we have no output, right, because there's nowhere for the current to flow, so this LED is not being lit up. The same thing goes for the next case, right, where S1 is closed and S2 is open, right? Since S2 is open, the circuit is still broken because these are in series, and so we still have no output. Now, for the last one, if I press S1 and S2 at the same time, I will now have a continuous line for my current to flow through, and so I now have a closed circuit, and that means I now have current running to this LED. So I do now have an output, or this LED is now being lit up. So then I have a 1. Now, referring to your charts, right, and looking at this output, we can see that this type of gate, or this circuit that we built, functions as an AND gate. Okay, so the very first circuit that you'll see is an AND gate, right? So this is a very simple AND gate. The next one over here is we put these two switches in parallel, and we'll see by how putting these in parallel will now change our truth table. So our options for our inputs are still the same, because it can either be open or closed, just one or the other. Now, if both of these switches are open, we still have no output because the circuit is broken at this point and at this point, so no current can flow through this part of the circuit. And so our output here is 0. Now, if I close switch 2, that means the current can flow through this bottom half of this parallel circuit, right? Just because S1 is open doesn't mean anything because S2 is closed. So if S2 is closed, then the current can flow through that branch of the parallel switches, and then I will get some output on my LED. So my output here is 1. Now the same is true vice versa, right? If S2 is now open and S1 is now closed, that means my current can now flow through this top branch of my parallel circuit. It can flow through S1, which means I'm going to get some current flowing through my LED, which means I'm going to have an output. And now if they're both closed, right, same thing, I still have a closed circuit. Current can flow through this LED if they're both closed, and so again I will get an output 1. And then again, referring to either your manual or the video, or earlier in the video we did those truth tables. If you look at this output, you can see that this corresponds to an OR gate. So what we've seen here, what we've built here, it will be an OR gate. All right, and then coming down to these transistor circuits, these are a little bit more complicated to understand, but really in the grand scheme of things, they're only a slightly more complicated, right? Because for a transistor to be on, right, to not be in the cutoff region, we need this base emitter voltage to be at least 0.7. Okay, so I mean, I need some current running to this base, or running from this base, or I need some voltage at the base, right? And we can see we have two switches over here, two switches for transistor Q1 and Q2. If this switch is open, if the switch is open for Q1, that means my base is going to be grounded because I have a ground here, which means my base emitter voltage is going to be 0, which means this transistor is in the cutoff region, or it's off, which means I cannot have any current running through this transistor. So unless I have some voltage at the base, these transistors just act like an open switch. Okay? So keeping that in mind, let's now do the truth table here. So we have 0, 0, 0, 1, 1, 0, and 1, 1. Right, in the case where both Q1, transistor 1 and transistor 2 are both off, that means current cannot flow across this path, right? We're applying a voltage at the collector here, so current cannot flow through this path, which means my LED is not lit up because both of these are off. So my output is 0. All right, if Q1 is off but Q2 is on, right, the current can flow through Q2, but it'll be stopped by Q1, right, because Q1 is off. Okay, so we still have no output going to our LED down here. The same thing is true if Q1 is on and Q2 is off, right? If Q1 is on, then yes, current can flow through this transistor Q1, but since it can't go through the Q2, then the current can't flow through this path and the current can't reach the LED. So we still have 0 there. Right, so only in the case where both of these transistors is on can current flow from the top here to the bottom ground here and flow through this LED. So in the case where they're both on, we do have an output, which means that, again, this is an AND gate. Okay, so it's a little bit more complicated way of building an AND gate to what we built with just the switches. All right, and now the final one that we'll be talking about is this over here. And all we've done is moved the diode from here at the emitter of Q1. We've moved it to the collector of Q2. So we've moved our output up to this point here. All right, so let's see what moving our output does to our circuit. So let's rewrite our inputs, our possibilities for our inputs. So if Q2 and Q1 are off, right, and we have some current flowing through this resistor up here, right? If Q2 and Q1 are off, this branch here at this node, right, no current will run through this branch because Q2 and Q1 are off, so no current can flow this way. So all of the current will flow this direction across our diode, our light emitting diode. So we will have an output if they're both off. Okay, if Q1 is off and Q2 is on, again, that means no current is going to run into the transistors because there's no current can flow into this branch because Q1 is off, which means, again, all of the current is going to flow across the diode at this junction. So again, we will have some output, or this LED will be lit up. And similar to that one, we will have an output if Q1 is on and Q2 is off, again, for the same reason, no current can flow through this branch, so all of it flows through the diode. And then finally, if Q2 and Q1 are both on, right, that means we now have a short circuit from this point to ground, which means at this point, the current's not going to want to go across this diode. It's going to want to go straight to ground because this is a short circuit here, right? So all of the current is flowing through this branch now. None of it's going to be flowing across the diode, so we actually have an off if both of the transistors are on, but we have no signal from our diode or no output if both transistors have been turned on. Okay, and now looking at your manual, you can see that this output corresponds to a NAND gate. All right, so we've seen how we can, using some simple circuits, be able to build these. We can build these different gates, logic gates. All right. You will also see that there's going to be some integrated circuits. And integrated circuits we can think of them as black boxes. So we don't have to worry about what the internals of these things look like. We only have to worry about if I input two things. If I input two things to the black box, what am I getting out? Okay, so you'll be given various integrated circuit numbers along with the truth tables corresponding to those circuits that you'll see us you'll see us determine how to get those truth tables in the next part. And then from those truth tables, it'll be your job to determine what type of gate those integrated circuits are. Okay, So that'll be the next part is you'll see us first building these 4 circuits and showing how they work, and then the last part will be taking different integrated circuits, putting it into our larger circuit, and then determining what these truth tables will be, so that you will then be able to determine what type of gate that particular integrated circuit is. Okay, so that'll be it for this part. Next, you'll see us in a lab with these built circuits, and we'll demonstrate how they work. Okay, guys, in this part of the video, we're going to be demonstrating part A for your logic gates experiment. And so what you can see here is I have both of the gates built. So we have our AND gate, where these two switches S1 and S2 are going to be in series with each other. You can see we start from a power source here, come down, it goes through this switch, comes up through this switch into our LED here, and then to ground. So both of these switches are in series, which means this is our AND gate. Okay, you can see over here both of these switches are in parallel, right? They share an end here, and then they share an end up here. Here's our LED for that one, and then we have power being supplied to this one. So right now power is being supplied to both of our circuits using our variable DC power supply right there, right? So that's hooked up. Moving back to our circuit. All right, now let's see how we would have gone about getting these truth tables for this particular circuit. So focusing on just the first one, circuit 1 in part A, that series circuit, if we press S1, so I'm pressing S1 down, we can see that our light is still not illuminated. Okay, if I take that off, so this would be 1, 0, and we're still getting a 0 output. If I now do 0, 1 and press S2, we still have no output. Okay, now if I press both of them, so we have our 1, 1 input, that LED now lights up, and so we have a 1 output. All right, which means this is our AND gate, because 0, 0, 1, 0, and 0, 1 all gives us 0 for the output, and 1, 1 gives us 1 for the output. Okay, so that's your truth table and the circuit demonstration for part A, for the first circuit of part A. Now, for the parallel circuit, we have it hooked up to S3 and S4. So here are our 2 switches in parallel. All right, and this is going to be our OR gate. So right now we have neither one of them pressed, and you can see that we have no output. So that's consistent with our OR gate. If I press just one, S3, you can see that red LED lights up. So 1, 0 in this case has a 1 output. And now if I do 0, 1, so I press this second switch, you can see that also has an output. And then if I press both at the same time, we again have an output. So our truth table for this one would be 0, 1, 1, and then 1 for the output, right? Which is consistent with what we talked about for an OR gate. Okay, so this first part was pretty straightforward. It wouldn't have taken you very long to build either of these 2 circuits and to get these truth tables. So what you'll see in the next video after I build the circuit, the transistor circuit, is you will see part B. So we will be right back. All right, guys, we're back. This is gonna be, so we got the circuit built for part B here. You can see the 2 transistors there, and we can see our diode here connected to the emitter of Q1, and then going to ground. Right, and then we have all of our various resistors and stuff in there according to the circuit diagram that you see in part B. So let's go ahead and get the truth table for this particular circuit, and then we'll move our diode to the point labeled A in that circuit diagram, and then we'll see what the truth table becomes whenever we move that output point. Okay, so if we go ahead and press, well, right now we have 0, 0, and you can see that this LED here is currently off, so 0, 0 would have an output of 0. Now if we do 1, 0, and press that first switch, you can see that, again, we have no output for our LED. And if we press S2, corresponding to Q2, then again, we have no output. And then only when we press both of our switches at the same time do we get an output. Okay, so this first transistor circuit would be an AND gate, as we talked about in the introduction. All right, so now let's go ahead and change our output. So we're basically changing the position of this LED, right? We want the LED now to go, instead of the emitter of Q1, we want it to go to the collector of Q2, which is here. So we put that at the collector and then run that to ground. You can see we already have this wire here running to ground. And then we want to take where Q or where the LED was, and now just run this wire straight to ground. So we just inserted, we just took out the LED, put this wire just going straight to ground that was connected to the LED, and then we moved the LED to point A within our circuit and then ran the other end of that LED to ground as the instructions tell us in step 3. All right, now we're gonna go ahead and do step 4, the final step in part B, and just go ahead and get our truth table. You can see that the light is currently on even though we have both of these switches are open. Okay, now let's go ahead and close one of our switches. So we have the 1, 0, and you can see we still have an output. So a 1, 0 would still have an output of 1. If we do 0, 1, same thing, we have an output of 1. And if we press both of them at the same time, then only then do we have no output. Okay, so this would be a 1, 1, 1, 0 output for those 4 different possible input combinations that we have. Okay, so this corresponds to an OR gate, as we talked about again in the introduction. Okay, so that shows you how you would have, first of all, built and then tested this circuit, and then gotten the various truth tables. So what we'll do now is we will go ahead and build the final circuit in this lab, which is part C, and we'll try out various integrated circuits and get truth tables for those circuits. And it will be your job to take the truth tables from those circuits to determine what type of gate those integrated circuits are. All right, so we will be right back once we get that circuit built. All right, guys, here we go. We got the last circuit built here. So we can see our integrated circuit here. This integrated circuit is going to be the 4001. Okay, so that's how you'll reference this integrated circuit, and we'll get the truth table here in a second for that. But let's just look at the circuit for a second and try to make sense of what's happening here. Right, so we can see that we have our 2 switches here, and each of these 2 switches run to the two of the input pins on our integrated circuit. All right, then we also have our grounding pin grounded and our VDD pin being supplied by our power here, which is running to our variable DC power supply, which I will just not show. You'll just take my word for it that it's over there supplying power. And then what we'll do now is we'll press these switches, which will change the input going into here, and then we'll get a different output, and our output is running to this LED. So the output pin of our integrated circuit is running to our LED right there. Okay, so you can see right now we have 0, 0 as our input because neither one of our switches is being pressed, and you do see the LED is lighting up. So for the first output for 0, 0, you will have a 1. All right, now let's do the 0, 1 input. So if I press 0, 1, you can see the light goes off. Okay, so 0, 1 corresponds to a 0 for the output. Now if we do 1, 0, the light goes off again. So 1, 0 has an output of 0. And for the final spot on our truth table, if we press 1, 1, so they're both on, then you can see again that the light goes off. So only when both of them switches are open do we have an output. So you can use that information now to determine what type of gate this 4001 pin, our integrated circuit, is. So now let's go ahead and replace this circuit here. So we'll put even pressure on either end of it by pulling it out. And we're going to replace it by a 4011, so 4011 integrated circuit is going to go in next. Okay, so that should be good there. You can see that we do have the LEDs being lit up. So let's go ahead and do our truth table for this one and figure out what this guy is going to be here. Okay, so you can see that right now it is on. So 0, 0 has an output of 1. If I press 1, the output is still going. So 1, 0 has an output of 1. If I do 0, 1, again, we have an output of 1. And now if I press both of them at the same time, the light goes off. Okay, so you can use that now. So it's on unless I press both of them at the same time, right? So it's still on. If I press S1, it's still on. If I press S2, only whenever I press both of them does the light go off. So so it has an output of 1 unless both of our inputs are 1, in which case our output is 0. So yeah, you can now use that information to then find out what type of gate the 4011 integrated circuit is. And we'll do just one more of these integrated circuits, if I can get that out of there. And this integrated circuit here is going to be a 4070. Okay, so 4070. So let's go ahead and insert that one into the same place. So you can see nothing changes in the circuit, right? Because all of the inputs for all of these are the same. The only difference is what is it outputting, but the pin assignment is the same for all of these circuits, integrated circuits. Okay, so let's do this final one. This is again the 4070. So if I press, both of them are off or both of them are open. Both of our switches are set to 0 now. So for input 0, 0, we have an output of 0. For input of 1, 0, you can see that the light is lighting up there. So that means that we have some output. If I hit 0, 1 now, again, we have some output. So for 1, 0 and for 0, 1, we have an output of 1. And now if I hit both of them at the same time, I don't get any output. Okay, so I only have an output if I'm pressing either S1 or S2. If they're both off or if they're both on, I get no output. All right, so now you can again use that truth table. You can determine that truth table and then use that truth table to then find out what type of gate this 4070 is. All right, so that's going to be all of the labs. So really, this lab would have been probably the most straightforward all semester. It's not. The circuits aren't too difficult to build. Getting the data doesn't take too long, right? It's just determining the truth table, which is just pressing really like 3 or 4 buttons. And so really this lab is good. Your lab report should be mostly qualitative, just looking at the different truth tables and determining from those truth tables, first of all, did your circuits work? And in this case, for this final part, for part C, what is the actual gate for each of these pins, or for each of these integrated circuits? All right, so that'll do it for this lab's week, for this week's lab, and we will see you next week with your lab over SR flip-flops.